is to use sound science to drive policy. And I'm one of the science people. I am the director of coral conservation, which sounds very big, just because they don't have to pay me as much as they need their title. So I'm going to talk about potential effects of ocean acidification on coral reefs. Figure out how to work this thing. We'll do it easy, right? All right, when people think of coral reefs, this is probably one of the images that comes to mind. Gin clear waters, lovely, thriving, healthy reefs, and lots of fish. Now, this seems a little far removed from the Pacific Northwest, and indeed these kinds of reefs are. But today I'm going to talk about not only tropical shallow coral reefs, but another kind of coral reef, and one that I've been working on, focusing on for the last decade or so, and that's deep water corals, and I'll talk about those in a little bit. So shallow reefs, well, they're in the Pacific zone, they're less than 300 feet generally. They're warm temperatures, which means with a few exceptions, they're constrained to the tropics. Lots of light, of course, the photic zone. Their growth is slow to moderate. Some species grow relatively quickly, others very, very slowly, but generally they don't grow too quickly. They are primarily coastal, near shore, and Dick mentioned some of the problems, the issues that come from being near to human habitation. They are zooxanthellae, and feeding on light seems a little simplistic for this audience, but what that means is that they have symbiotic dinoflagellates in their tissues, and this is what provides this kind of dark brown or greenish color that you see in most tropical corals. The reef structure itself is created by stony corals, as scleractinia, and there are other associated types of corals, the gorgonians and the hydrocorals, that contribute to the reef structure but are not actually reef forming. The fact that they're zooxanthellae, they need these symbiotic algae. In the tropics, there is not a lot of food in the water column. These algae are critical to the coral's nutrition. They're little plants, they use carbon dioxide, they generate carbohydrate from it, energy from it, they use it themselves, and what is in excess goes to the coral. So it's a tight relationship and it's critical. Now, Brian mentioned sea surface temperatures or increasing temperatures. We're talking about ocean acidification here today, but evil twin of that, of course, is increasing sea surface temperature or sea temperature. Increasing temperatures causes that relationship to break down. It causes the corals to expel those symbiotic algae, and that creates an energy crisis for the corals. Now that's important because to produce their skeletons is an energetic process. They need energy. The corals need energy to produce their skeletons. If they're in an energy crisis, coupled with lack of carbonate from aragonite saturation loss, then it creates a double whammy for them to be able to generate their skeletons and grow. So their access to food is very, very important. And they're restricted to the tropics mostly. So these are deep examples of deep coral reefs. Well, the top one is not a reef, it's a tree coral. Now, deep corals fall broadly into these two categories. One is the reef building. So the bottom one is Lophelia pertusa. It's the most common globally, almost globally distributed deep water coral. It's a branching coral, it's a stony coral, and as it grows, it forms these big colonies that over time the inside sort of decays and dies, the outside carries on growing, and they form these large biocombs or reef structures that are actually analogous to shallow water reefs. And so these are the real reef builders or structure formers. The tree corals perform the same role as they do in shallow reefs. They just contribute to the structure of the young coral reefs. So deep reefs are between 350 and 10,000 feet, so these are real deep. They're cold, there's no light, so they don't have zooxanthellae. They rely on the input of detrital material from the water column or from zooplankton. And we've heard about possible impacts on zooplankton ocean acidification. This is an indirect impact on the species. They're usually offshore and high seas, so they're not subject to coastal inputs. They're very, very slow growing. They are zooxanthellae, as I've said, and they're globally distributed. So it seems like they would be more disjunct from the effects of ocean acidification. You know, they're offshore, they're deep. But as Dick mentioned, the problem is that carbon dioxide dissolves more easily in cold water. So these guys are dealing with a high level of carbon dioxide in their waters naturally. So as the global system becomes more and more influxed with CO2, these deeper waters are going to get more and more carbon dioxide, more and more acidic, and less carbon. This I just put in to remind me to tell you that some of the most diverse, beautiful, and abundant corals are right here off the Pacific Northwest. This is actually a picture of the coral gardens in Alaska off the Aleutian Islands. They're absolutely beautiful. The biodiversity is off the charts. We also have abundant and not structure-forming gorgonians off the coast here in the Pacific Coast National Marine Sanctuary. So we do have corals out here. We have them all the way along the shelf and slope down to California, and they provide habitat for commercial fisheries species. So they are important to the Pacific Northwest. So this just reiterates what I was saying about the distribution. If you look at the red, that's where the warm water reefs are for the most part, and the cold water reefs are in the North Atlantic, in the northern hemisphere, and then in the southern hemisphere, primarily over by Australia. And this is, I just want to remind you of that. Now, if you look at this, it's kind of a bit noisy, but we've all had caffeine and sugar, so we should be able to grasp this. The middle section where all the blackness is, that's where all the shallow water corals are. Now, if you look at that color, it's mostly the green. If you go down to the color bar, it's between marginal and adequate. Now, this is a projection, but not too far into the future. 2040 is not too far away. This is what we think our shallow water corals are going to be dealing with in surface waters within the next 30 years or so. So it's still okay. You know, it's not optimal, but they're hanging in there. If you look at this, however, the projected for the 2100s, that's looking pretty grim. We're on the low to marginal end throughout the tropics. And this is where the corals are going to have a really hard time trying to keep up. Now, the corals can calcify under undersaturated conditions for a short period of time. Some species can. But in general, in a scenario like this, they're going to be in trouble. The reefs are going to be in severe trouble. So for deep corals, we're not so interested in the surface waters, of course, but this kind of fuzzy picture, I apologize, it's a little pixelated. It shows the aragonite saturation depth. Now, the take-home message of this is that the depth of the aragonite saturation horizon is the depth above which we're saturated. So we want a deep saturation horizon. That's a good thing. Now, the blue is 2,000 meters. So, meters or feet? Meters, right. So the tropics, where the shallow water corals are, they're looking good. The tropical surface waters, they don't absorb as much carbon dioxide, and so surface waters are okay, and the deep waters are also okay. The aragonite saturation horizon is nice and deep. But where the deep water corals are, primarily the North Atlantic and over by Australia, you can see that the aragonite saturation horizon is getting shallower. It's relatively shallow. Again, this is projected 2020, which is only a decade from now. And the aragonite saturation horizon is going to be 100 meters. So that means that a lot of those deep corals are already on the edge of undersaturated water. So if we look forward to 2099, it's looking even worse. That saturation horizon is shoaling. It's getting shallower and shallower. So a lot of these deep corals are going to be in undersaturated conditions, and that means they're going to be fighting to try and make their calcium carbonate skeleton. So just to sort of reiterate what I've just been saying, the possible effects of ocean acidification on both shallow and deep coral communities is that they reduce their calcification rates. It's harder for them to calcify in a low carbonate situation. And by the way, a lot of the scleractinians are the ones that are reformers use aragonite to create their skeletons, which is one of the most soluble forms of calcium carbonate. Some of the other hydrocorals use calcite, but the stony corals use this relatively soluble form. Now, you've heard from the speakers earlier that biological systems have a lot of variability. Of course, that's true in coral reefs as well. It's highly biodiverse, and therefore lots of different species. And you have lots of different tolerances. So what ends up happening in any kind of situation like this is that the susceptible species drop out, and you end up with the weedier or the more tolerant ones, which, you've still got an ecosystem, but it doesn't have the resilience that a diverse ecosystem would have. So you get this change in community composition, and the effects of that really aren't well known. Changes to food supply to deep corals, the changes in zooplankton, the surface productivities, these all change things. Now, it might not necessarily be a bad thing in some cases. I've worked down in the Gulf of Mexico, which is the thriving coral reefs there are right underneath the Mississippi outfall, the outfall from the Mississippi River. Tons and tons of organic material. So, sometimes maybe surface productivity might be a good thing for these ecosystems. But the thing is, we don't really understand how they work, so we can't really predict too well what will happen under different scenarios. So eventually, even the tough corals, even the ones that are resilient, as the carbonate ions get fewer and fewer and other changes happen, they won't be able to hang on. If you're using energy to produce calcium, you're not using it for growth and reproduction, which reduces the long-term viability of the ecosystem, and as I said, eventually they'll reach the point where they just can't compensate, and the ecosystem will die. And since corals are the foundation of the ecosystem, then everything else associated with it is going to suffer too. So we'll end up with the loss of global biodiversity in the story. So there is some good news. For now. All right, so tropical waters are not going to, they're going to be slower to become undersaturated. But as we know, tropical coral reefs have a lot of other stresses and problems. Some deep corals survive below that aragonite saturation horizon naturally. That's just where they live. If the animals get enough food, maybe they can compensate for this added stress of deep calcification. Maybe they can adapt, use a different form of carbonate. We just don't know. There's work going on to investigate that, but we just don't know. And maybe we'll end up with the calcite users instead of the aragonite users dominating the ecosystem. So there's lots more bad news. We've already set this ocean acidification process in motion, so we have to face the consequences of it. We can't just stop it now, it will continue. Tropical reefs are also being hit by sea surface temperature, which is going to add to that stress. So they're going to get hit twice. So even though acidification is not as much of a problem, they're going to get hit with sea surface temperature issues, and that's going to put them under stress. There's always limits to the way to adaptation and resilience. Species will be lost, and even though nearly all these deep reefs are currently above that aragonite saturation horizon, as it shoals and becomes more shallow, they'll be in undersaturated waters. And the thing is that the live corals can compensate. They create internal chemical reactions that allow them to lay down calcium even in undersaturated waters or in low saturation states. However, the reef structure is composed of a lot of dead corals, and that has no protection whatsoever, and so it will dissolve. So you'll undermine the structure itself, even though the live corals might not survive. So what can we do? Well, stop burning fossil fuels. Of course, we all know this, and we all know how hard that's going to be to do. So, as Dick said, up here, 25 to 49% of the ocean acidification is from this anthropocene, this global situation. That still leaves a chunk that's not, that we can maybe address through local means, such as addressing local coastal pollution issues, reduce nutrient input, reduce the physical damage. A system under stress from chronic stress is going to respond poorly to an additional stress. It's somewhat like somebody with cancer getting the flu. So what we can do is try and improve the health of our ecosystem, reduce the local sources so that they can have more resilience against this global phenomenon that is bearing down on us. Marine protected areas is one tool that we can use, as well as better coastal management to maintain the health of these systems so that they can better